Okay, so hi. Let's see, this guy, get rid of that. Okay. Let's see. So that's good. All right, so I want to go through the quiz. I thought, excuse me, I thought it was kind of like a challenging quiz, but the answers I looked at seemed pretty good, so I guess it was maybe not that challenging. Let's see. Open this over here. And then open this here. So this is kind of a popular item for a while now. This lipid technique. So it started. The guy at MIT, this Ned Thomas, who moved to Rice University to be head of the nano. They have a big nano center there, and then because nanotubes were discovered, I guess, at Rice in Houston, right? And then anyway, somehow Rice became the center for nanotechnology, and this Thomas, who was doing this lipid stuff, moved there to head that center. He did this work. He had a big center at MIT that was like a military center, so they're interested in this kind of high-speed impact, basically bullets hitting things. I think it was an Army-funded center, big one. Like it was bigger than a DARPA project, so I think it was in the around like hundreds of millions of dollars center. And then I think he took some of that to Texas with him, and now he moved from Rice recently to Texas A&M. He's still doing this lipid thing, partly. He's a microscopist. So anyway, they have a sheet of some kind. I'm not sure what this is. They put the material on, but then they have a pulse laser, something like what Vasudevan has this pulse laser center. The what's it called? Laser peening. So he's shooting this pulse laser at metal to, peening means you throw ball bearings at a metal to toughen the surface by impact. And they can do that with lasers. So you blast the surface with lasers. It causes rapid heating, and that causes like a shock wave, right? So they're using that same kind of laser. So it's kind of a violent measurement, in other words. So you heat up this thing with a pulse of a laser that destroys the thing that a little bead is sitting on. That launches the bead at 200 miles an hour at your sample, and then it basically will penetrate the sample either kind of brittly or ductily, and so you can look at post-mortem images of the surface to see what happened, and you can also have a high-speed camera that can photograph the particle blasting through the polymer that you have here. So this is usually to test polymers. So in this paper by Souls, he doesn't talk about this much, but when he presented this at the ACS, he talked about this impact testing. This is one of his slides. And the paper that he's referring to is this paper, the 2021 macromolecules, where he's doing quasi-elastic and inelastic neutron scattering to look at what happens to the material under these high-speed impacts. Like what's a molecular mechanism for this transition from a ductile to brittle behavior. So it turns out polycarbonate is a great material for this. It's got a huge energy absorption when this particle flies through it. So for that reason, it's used in bulletproof glass. So you have layers of glass and layers of polycarbonate, and then glass becomes brittle because of surface flaws. So if you coat the surface with this polyvinyl butyrol polymer, it'll deactivate the surface, so it's harder for cracks to initiate at the surface, making the glass like super glass. And then the polycarbonate. So it turns out like 2 layers of polycarbonate can absorb like 10 times as much as one layer that's twice as thick. So the more layers you have, the better. So they tend to make multi-layers in this bulletproof glass. There's a company in north of Cincinnati that makes bulletproof cars, and they do this kind of thing. There's a local company that's involved in this kind of ballistic production of modification of cars to make them. It's kind of interesting. It's UC graduates that are working there, so they've come and given talks before. Anyway, so basically the study is about this kind of material. So I stuck that picture in, even though the paper is a lot more kind of difficult. Right, so the paper is this paper, and he's showing this is a mean squared displacement. So this is obtained from the broadening of the peak of the scattered peak, and then he's plotting that against temperature, and you find out there's a transition from this brittle behavior to tough behavior. So you can pick out a feature and that goes along with this kind of behavior that you see in this this ablation lipid explosion kind of measurement. All this stuff is funded by the military. There's no peaceful use for this kind of thing, so in that sense it's somewhat tainted, but anyway, but the Army and the Air Force and the Navy are all really interested in these lipid measurements, even though this doesn't really, so 200 miles an hour isn't really fast enough to model a bullet. Right? A bullet goes a lot faster, but basically it looks like a bullet. So I think they dump money into this. I think Souls isn't doing it because of the military. He's doing it because he has a machine. So they have machines at NIST. They have neutron scattering. So they have a quasi-elastic neutron and they have inelastic neutron. So they have 3 or 4 machines that do this kind of measurement. So similar to what's at Oak Ridge, right? So, I mean, Oak Ridge has a much broader suite of instruments, but NIST has a fairly robust one and one that's well respected. In other words, it's kind of trusted, better than the Department of Energy one. So that's where things stand. So anyway, it turns out that the features that you can see in this kind of neutron measurement can also be seen with Raman scattering and this Brillouin light scattering, which are almost the same thing, right? So the question is like, and he does Brillouin light scattering, right? So he does that measurement, and then he compares what he gets from that with what he got from this quasi-elastic and inelastic neutron scattering, and it turns out they're comparable, right? In other words, he gets that in the when he does this business. So from the Brillouin scattering, he can get the deformation of the material in terms of like a compressive, like a longitudinal wave, which means it's a compressive wave. So like a sound wave is a longitudinal wave. So when sound progresses through air, the air compresses, it gets dense, and then it gets less dense, right? So it's kind of a density wave, a longitudinal wave, versus a wave you see in the ocean is a shear wave. So when they go up and down, so that's different than the longitudinal wave. So one is going to be like the bulk compressibility of the material, right? And then the KT is kind of moving it back. And then the other is the shear. It's a shear. So if you take the ratio of those two, which you can, so you get a peak in Brillouin scattering for each one of those, take the ratio of the two, you get Poisson ratio. And it turns out that's important to brittle to ductile because Poisson ratio is for a brittle kind of compressive material like a foam is 0, and it's 0.5 for something that's Hookean, right? So basically, so brittle material is going to have a larger, I guess, a smaller Poisson ratio than a ductile material. So I think I said that backwards, but anyway. So anyway, this change from a fixed number, then it increases from this Boolean scattering, which is almost like a mechanical test, compares well with this broadening of the peak that he gets. Right, the broadening of the peak is here. So he's got a so you're coming in with a beam of neutrons, and then you're picking it out at some value Q, right? So theta and Q are related, and Q is also related to energy because it's this is Q is the momentum, right? So momentum times the velocity is going to be energy, like kinetic energy. Right, so Q is kind of a measure of the energy also if you multiply it by the velocity. So anyway, so but 1 over lambda is like h nu is like energy for light. So you can kind of say that that this term is energy and this term is something about the direction that the beam's going. Right? So you have your sample here. Beam comes in like diffraction, you measure an angle. So you're going to pick up a signal here. So that signals, so you came in with a certain wavelength, lambda, and if it's elastic, it comes out with the wavelength lambda. If this material's moving around, then the velocity of whatever the thing it hits. So the beam comes in, it hits the thing, and then the thing, so this is oscillating, the thing oscillates, and the thing regenerates. Right. So if there's no energy loss, then that oscillation is the same as the oscillation that comes out. It means the wavelength and the wavelengths are equal. But if there's an energy loss that goes on here, this wavelength can drop or increase depending on what kind of energy loss happened. Right. So that means your wavelength would change. So that means if you plot out the intensity versus the energy, which is related to the wavelength, then you'll see that this thing goes from a sharp peak, like monochromatic, and then broadens out. And there's two kinds of broadenings that happen. One is just the Debye-Waller broadening, so you get just the peak gets broader, and the other kind is quantized, it's at a fixed energy value. So quantized transitions are like you have a bond. It's in the way. So say you have a bond between two atoms and it vibrates. Right? So it can do different kinds of vibrations. Those vibrations of a bond, because they're atomic scale, are they have a fixed energy. It's the energy of that vibration, right? So if the beam comes in and it's about the same energy as that vibration, then it can either, if that thing's already vibrating because of KT, it can absorb that energy. So you can have your peak here, and then it can get a higher energy, right? That's called anti-Stokes. And it can also absorb the energy, so it'll shift it down. That's called Stokes. So it's more likely to get a Stokes than an anti-Stokes. In other words, losing energy to the beam is easier than gaining energy from the material. Right, so you're more likely to get a Stokes, so that's kind of a bigger peak. And then the distance and energy between the peak that came in and what came out is the energy of that absorption. So that's an inelastic spectroscopy or scattering. And if that, so depending on what that thing is that transferred the energy, that's the difference between Raman and this Boolean light scattering. If it's a bond the way I did it here, then that's Raman. So if you're looking at a bond vibrations, then that's Raman scattering. If you're looking at a crystal, okay, so you have some kind of crystal, and then those called lattice vibrations that happen. Right? And those can be longitudinal or transverse. In other words, it can be a compressive wave like a sound wave, or it can be a shear wave. right? So anyway, if you're looking at a lattice vibration, then you call that a phonon, right? So phonon is like motion of atoms that are quantized because they're atomic size. So their quantum mechanics governs it. So they're fixed energy. Because they're fixed energy, it's inelastic scattering, and the different kinds of phonons that you can talk about lead to different peaks in this, right? So basically that's, so you're doing the same thing in Raman and in Brillouin scattering. The difference is the material, like what the material is, it's absorbing it. So if it's just you can put an organic liquid in and it will have Raman peaks, quantized Raman peaks because the bond vibrations are quantized. Or you can put a crystal in and it'll have these phonon peaks. You know, the measurement's the same thing. It's just like what the thing you're looking at is different. And that the machines are designed to detect these different kinds of energy absorption phenomena, right? But they're all quantized and they all give rise to basically a peak. It doesn't look like much of a peak, but it's a peak according to what we're talking about here. It's not considered this broadening. So they can distinguish between those two by curve fitting this and by using a function for this broadening, which is this Debye-Waller function, which looks exactly like Gounier's law, strangely enough, right? So, and it's not that strange because this is a Gaussian function, right? So that Gaussian curve is like your general fall behind, like anytime you see something that leads to kind of randomness, you're going to use Gaussian. I mean, like a grade distribution, you use a Gaussian distribution, the bell-shaped curve, right? So that's your fall to answer to anything that looks like you have a sharp thing and it becomes broader. You say, oh, it's Gaussian. That's the first thing you do, right? So it's not surprising that this thing looks just like Gounier's law because they're both talking about random things. In the case of Gounier's law, you're talking about a structure, so some odd structure, and if it's isotropically moving around, then kind of the electron density of that thing kind of looks Gaussian, except it's got fixed size, so it truncates, right? So you can model that broadening of the electron density as a function of size due to kind of thermal motion of a randomly shaped object, or it could be a Polymer coil. It can be anything that's rotating ends up being a Gaussian. I mean, even if it's a perfect sphere, because you're coming in with a beam and then you're looking at what's the density away from a point that was already in the sample, so this distance r. So your starting point would be at different points in the material. So even if it's a perfect sphere, it can have starting points that range. So you'll end up with basically a Gaussian cloud if it's moving around, it's thermally moving around, right? So the truncation will be sharper for a sphere than it will be for an odd shaped object, right? But it will be broader for a Polymer coil. But it turns out the truncation doesn't matter that much as long as you're looking at short distances here. So in this region where Gounier's law applies, it's okay. And the same thing goes for these phonons, right? I mean, the atoms are moving, but they're kind of restricted in space. So they're also going to have a truncation. So maybe this Debye-Waller factor could fall apart, similar to how Gounier's law falls apart. So the link between the two is they're both talking about some kind of random thing. So you fall to a Gaussian or bell-shaped curve to describe it. The distinction between the two is what causes the bell-shaped curve. Here, thermal motion is causing it, and here, just kind of the random isotropic choosing of where you start describes it. Now, it's exactly the same function. That's the kind of thing that should make you think about this, right? So it's exactly the same function. It's q squared rg squared by 3 negative exponential. That's the same thing as Gounier's law. Right, so anyway, so the reason 3 here is because it's 3D, and if you go back through Gounier's law derivation, the 3 is also because of 3D. So it's exactly the same thing. It's just like what causes the u squared are different. So it's almost like almost similar to the BLS and Raman. It's like what you're looking at versus what, so the function's the same, the technique's the same, but it's like what you're looking at distinguishes between what you call it, or what, how you interpret it. Right, so here you're interpreting this as the mean square displacement, okay, of what? Of a Brownian motion, right? So that's what links together the QELS and the dynamic light scattering, is that they're both looking at like Brownian motion. So once you realize that they're both looking at Brownian motion, then just like Wikipedia Brownian motion, you find out that the solution to the diffusion equation for Brownian motion is this, guess what, like a Gaussian, a bell-shaped curve, x squared, exponential minus x squared, then the sigma squared, which is sigma squared is this mean free path, is this 2 dt, the diffusion coefficient. Right, so Brownian motion, all these things are kind of linked together. That's the point. They're all like kind of confusing, but they're all like pretty much the same thing. So once you learn one of them, you should start to become recognizing certain features, and it will make your life kind of easier, right? So you have a particle, it moves around, and then you want to say, well, after all that motion, then what's the density of that particle as a function of the position? So it started at 0. And guess what? If it like randomly moves around, it's most likely going to be at 0. And like it's less likely it's going to go very far. So that probability will drop down. And then it's basically going to follow a bell-shaped curve. Right? So it's going to be like exponential minus x squared over 2 sigma squared. That's the bell-shaped curve in 1D. Right? So in 3D, it's going to be 3 times that, because the 3 probabilities will be 3/2, right? And then there's some prefactor that normalizes it. So the integral of this thing's 1. So the total probability is 1. So you'll have a prefactor, which will be the integral of that. So anyway, that's what the prefactor is here. There's a bell-shaped curve. For dt is the 2 sigma squared. Sigma squared is the mean free displacement, which is the thing that you're measuring in the Brownian of the peak. And then dt, d is what you measure in the quasi-elastic measurement. In other words, this equation, the relaxation time is 1 over dq squared for the, so the correlation function is exponential minus t over tau, the relaxation time. And then you get the diffusion coefficient, and from the diffusion coefficient, you get the hydrodynamic radius. Right, so everything is like linked together through the word Brownian motion. Right, so you can either do a measurement to measure, so you only need one number to get RH here. Right, the one number could be x squared, because if you get x squared, then you can get d. If you get d and you know the temperature, you can get RH, and you know the viscosity of the solvent. And then, or you could measure tau and the DLS and then get D and then D to RH. Right, so the two techniques can give you exactly the same answer. So again, like when they invented this thing, people thought, well, it's going to be a heck of a lot easier to measure this peak broadening, than it is going to be to measure like a particle flying around, then how the light flickers. Right, because doing the transform of that before you had computers, right, it wasn't really that easy, because your limitations on time are time equals infinity and time equals 0. So your limitations of your measurement are going to be able to do a measurement at 0 time, which is not possible, and to do a measurement at infinity time, which isn't possible. So you have to truncate the transform that you're going to do, the Fourier transform, which is going to be an integral of E I dot whatever time, I guess, to get the frequency. So dt, right? So your time has to go in this integral to infinity from 0. Right? So if you truncate these things, then your Fourier transform gets messed up. Right? So you have to do this measurement forever. Then you have to do it from 0. And then you have to, once you're done with it, you have to do this integration numerically, like you take the points separately every two possible pairs in this. So if you go into infinity, you're going to have a gazillion pairs, and then to find all those pairs is going to be like squaring gazillions, which turns out to take a long time. It takes forever, right? So originally I thought, well, this QELS is the way to go. And then some really bright people who were good at chemistry and good at figuring out this math and good at computers worked out how to do this. And it turns out you can do this instantaneously, almost instantaneously. And it turns out this QE, quasi-elastic light scattering, you have to, your limitation here is measuring the breadth and energy of this thing, and your resolution isn't that good. Like, in other words, how are you going to do that? So you're going to put in a grid, you're going to spectrally separate into a rainbow, you're going to get energies from that. That's limited in what it can do. Or you're going to do a Michelson Morley, or a what's it called, interferometer measurement, right? So you take the beam, you put it through a mirror, and then you move the mirror X, and then you get a fringe pattern by recombining the beams. So there's some limitation in resolution you can get by the distance that you can move a motor relative to the wavelength of light. Right. So it turns, and so the interferometer isn't a bad way to go, but this thing's faster. The DLS is much faster and much more robust. Right. It's much easier to do. Right. So you always get an answer from a DLS. This thing is less, there's a lot more opportunity for noise and things in this, because you're doing a spectral analysis. So it's not going to be as clean. Anyway, so that's probably more than you need to know, but basically, like as far as like the qualifiers, which of course is supposedly tuned towards, like, you should know all these things. Like, these are all basic tools in polymers, right? So, but if you're going to work at a polymer plant or something, maybe you don't need to know it. But DLS is definitely something you'll run into because it's so easy to use. So the DLS is going to cost you 10 grand, right? It's cheap for an instrument that can measure nano size. This is going to come out with sizes on a nanoscale, like 10 nanometers, maybe less than that you can measure, maybe 8 nanometer, right? If you want to look at a comparable instrument that can measure the size of something at 8 nanometers, it's going to be a high resolution TEM with cryo attachments, or you're going to look at it at like a synchrotron. So all those things are going to be much more than millions of dollars. Right. So something 10,000 can do the same thing. That's a pretty good deal, and it works every time. And you can stick anything into it. You can put paint into it, you can put milk into it. You can basically stick anything into a DLS as long as it goes into solution. So this is like, so biology, everybody uses dynamic light scattering. So this is a kind of go-to tool. It's a foolproof method. QELS less so. So why is it that they didn't use DLS in the synchrotron when the neutron measurement, right? Because if it's so much better, why didn't they just use it here? Why are they going through this spectral analysis? And the reason is that the frequencies here are milliseconds. Like, the diffusion coefficient is going to say that the particles move around on a millisecond timescale, which is something that you can measure, right? You can measure milliseconds pretty easily with the correlator. Over here, I mean, if you look at the spectrum, I'm not sure if he shows it in this paper. So the time scale is nanosecond to picosecond. That's fast. That's like so fast that you can't believe it. Right. So he's talking about molecular vibrations, molecular motions. They're really fast. So you're not going to see a scattered pattern like this, the thing jogging around on a millisecond time scale. It's just going to be gone before you can even think about it. Right. So there's no instrument that can measure on that speed of vibration. So you can't do a dynamic light scattering measurement with neutrons because it's too fast. But the broadening is fine. So you can see that they can measure the broadening. Right. So anyway, that's why they probably would prefer not to do this kind of measurement, because it's, look how sketchy it is. You know, it's too mushy. Like, you're just doing these multi-parameter fits to this broad blob, right? Whereas in DLS, you see a nice exponential decay. So if you have complicated systems here, they tend to smear into it. In QELS, complicated systems, it breaks it apart because it's a Fourier transform thing you're looking at. So it tends to naturally like break apart complicated things. So DLS is like a much better technique to use, even though it looks like it wouldn't be from the first point. And then, all right, so let me go through this now. Anyway, so I think it's kind of an interesting application of what's going on, because it has to, if you're interested in the military, it's kind of like blowing things up, you know. So some people, this is appealing. And then from a scientific perspective, it's interesting that they can get this relationship between something that seems to be pretty weak in terms of hardcore understanding and something that's very tangible, like brittle ductile transition. And they see a strong signature, right, between these boson or phonon vibrations due to the inelastic, and then this quasi-elastic, which has to do with motion of the molecules. So like this business of chain scission versus shear and disentanglement of the chains is the answer to this brittle to ductile transition in polycarbonate. And then the important thing is that they get ductile under the speeds they're interested in this lipid measurement. So that's why polycarbonate is better than polystyrene. It doesn't have that signature. At some point, not in this paper, but Souls compares like different polymers and shows that basically polycarbonate has a special feature here, that this brittle to ductile transition happens. So let's see, so boson. People did well, like putting this together. This is complicated, I think. So I think the answers I got were pretty good. Some were excellent, you know, for as far as like how you guys took this apart. So it's good. Like I was kind of surprised. I thought you like, oh, can't answer it at all, but actually people did really well. I think some people, a couple people have some background in this area. Like, whereas if you took thermodynamics, like kind of materials thermodynamics, the high level part of it, or you would have already known about these lattice vibrations and things. So that's taught in chemistry and quantum thermo, or it's basically the basis for the understanding of heat capacity in solid state. So anytime any metals or anything, metallurgy, you would have this stuff possibly. So that could be why. I'm not sure, but basically that could be why people have seen it before. Otherwise, they're just good readers of Wikipedia. You know, this stuff is all in Wikipedia. But it's not necessarily understandable. You know? So I think I answered that. Dynamic light scattering. I mean, the reason where this function comes from, so basically you can work it out. Like it's derived on Wikipedia. Like if you go to the Debye-Waller factor, they do a derivation of it, more or less. Like they skip a few steps. Basically, I kind of wrote down in 3 or 4 lines what that derivation is. So I think I mentioned that, and then the Poisson ratio thing. So oh yeah. So I did have that. So the gel is 0.5. So what that means is, so incompressible means that, so if you take something, so liquid is usually assumed to be incompressible, and a gel is basically a liquid with a network. Right, so gels are incompressible. It means if you pull it, right, so you pull it like in the X direction, then it has to come in the Y and Z. Right, and if you look at only one, like Y, it's going to be 1/2. So 1/2 plus 1/2 for Z gives you X. Right, that means the material is totally incompressible, like a rubber. A rubber is incompressible. Most polymers, you assume they're incompressible. Right, so the first guess is 1/2. And then something that's compressible doesn't have that feature. So if you take something like a metal, right, and then it can only deform like 1% if you're lucky. When you deform it, you're actually stretching the bonds, right? So your bond A goes to A plus delta A. right? And there's no reason that it would want to take from B and C because it's changing the bond length in the A direction. So that's the case where you're going to have like cork or foam. There's going to be there's no response. If you pull an X, there's not going to be any response Y and Z. It just stays the same diameter and you can just smush it, right? Like foam, like these tension balls, you know, that you squeeze. So it's basically a foam. So it's not going to, its Poisson ratio is going to be 0. There's going to be no response in X and Z. So anyway, from that you can kind of say like it goes from glassy to gold or whatever. Right. So that's it for E. Any questions on that quiz? That was pretty good. Actually, it was okay. And with the answers, I thought the answers were good. So I think it was kind of worthwhile, even though it seemed questionable at the beginning. Like I wrote the quiz up and I thought, wow, this is too hard. Like this one isn't really going to fly, but turned out it was okay. NIST is doing pretty good work. Like the more I see, there's pretty good things going on at NIST. This Souls guy is a group leader. Jack Douglas is a theory person in polymers. He's pretty much the smartest theory guy around. And Albert Yee is an old guy from Michigan, but now he's at some other place. He's mechanics. He does like mechanics. I mean, he's like one of the old people. I don't know where they say he is. I don't like how Macromolecules puts the locations at the end now. They used to put it up front, but so Yi is at California. But before he was at Michigan. He's like a standard Michigan guy. I don't know any of the other people. But basically, it's a pretty good group that's working on this. All right, so anyway, the next thing, if there's no questions, is to look at this polymer response to perturbation. So polymers have kind of a unique or different ability, right? So you have, and the easiest thing to talk about is if you pull it. So you have this long chain, or you take the long chain and you put it on a surface. So you tag one end and then you stick it to the surface. So what's it going to do? So you draw it and you kind of draw in what happens. So if you zoom in right here, or if you zoom in here, those two things look identical. So for small scale, it's the same. But if you look at a larger scale, so if you go up here, and then so you're going that way, then they're different. Right. So basically, between the same and different, there's a size scale, which you call this blob. You call that a blob. Means that you can take that chain and break it into blobs. Right. And you can say, like in this case, that thing is going to be ballistic. So it's going to be df equals 1 when you're above the blob size. And then within a blob, it looks the same as up there. So df equals 2 if it's a melt. Right. So you have a transition at this blob size between a rod and a coil. And you can see this, I think if you take this piece of string and you mess around with it enough, you'll see that it doesn't elongate on these small scales immediately. Right? So it'll be, as you pull on it, it'll go to this kind of structure. So it's got some kind of diameter for the rod, which is this blob size. Right? And the more you pull on it, so as the force goes up, that blob size goes down. As you can say, the blob size is going to be equal to 1 over the force that you put on it. So what makes it bigger? Right. So if it's actually a string, then it's kind of the spring constant, this K bending constant, that would make it bigger. right? And spring, like if it's a piece of fluff, right? Like a thread or something that you pick up, like it's a bending constant of the thread that makes it go bigger. And then the total structure of this thing is has to do with how it was made. It's trying to retain, just like a spring, it's just trying to retain the size of it. If it's a polymer, like a nanoscale polymer, so these things are moving around with KT, it's KT that's making it spring back. So the spring constant for a polymer is KT, right? It's some function of KT, like KT by NL squared, 3/2 or something, right? Or 3 KT over NL squared, right? So if you use the what we got before, the energy description for polymer, so this thing over here is going to be just like KT. The higher the temperature, the larger this size, right? So that's basically the idea of a tensile blob. So why would you want to know that? Well, you want to know if you surface graph chains, then you want to know what's the thickness, like what's the thickness of that layer. The thickness of that layer is going to follow this rule. It's going to follow this blob rule. So you need to know, in order to know the thickness of that layer, you need to know how large are the blobs. So you need to know what's the temperature, and then you need to know what's the force. So in fact, the thickness of that layer is going to be linear in thickness and temperature, right? So thickness is just going to go 1 to 1 with temperature because this dimension is 1 up to a point where the blob size becomes the entire chain, and then it's going to go to this Gaussian scaling for the expansion. So you'll see with chains tethered to a surface, you should see a thermal transition in the expansion coefficient for the thickness of that, right? So that's the first picture of how you're applying a field to a polymer, and it responds with a size, with like a special size. So here it's a mechanical field, it's a tensile field, and then it's responding with this size scale, this tensile blob size, right? But there's other kinds of fields you can apply to a polymer, right? In fact, in the first quiz, we went to that DiMarzio paper, and he kind of listed some of the kinds of fields. Like you can have a polymer that's going through a hole, right? And then we have this like entropy driven thing. And this, how it responds here, is going to be related to blobs, right? So everything you do to a polymer is going to be related to blobs in the end, even though blob sounds like an odd thing. The word blob came from Beaucage. So this idea of blob, that's French, right? So it sounds French. It's like some fluffy French idea about how things work. It turns out it can explain a lot of questions about how polymers behave. So tensile, you can do it a little bit more like analytically. You have the energy expression, you get the modulus. So you have force and distance described by this 3 kT over NL squared, the spring constant. All right, so you have NL squared is also a distance, right? It's an R, that's R squared. That's the coil squared. So you have R squared and R, that gives you a size. That ratio gives you the size. So you end up with force, and 3 kT gives you the size just from the force expression for a single coil. Right, so you'll end up just with this. So it's the same thing as you can intuitively get, that the harder you pull on it, the smaller that blob's going to get. And the higher the temperature, since temperature is what's causing the springiness of this thing, the higher the temperature, the larger the blob gets. Right, so it's that kind of makes sense. Once you have this blob size and you do calculations about what the thickness is, say, of those chains tethered. So when you tether the chains, there's not a tensile tensile force on it, but the planar forces generate kind of a tensile force. Right? If you push in on all sides and you don't push in on the vertical side, then the thing's going to act as if it had a tensile force on it vertically. It's a force kind of, it's a force difference that matters, not the actual direct where the force came from. If you pull on it this way, it doesn't matter if there's no force that way, but you push in all the other directions and kind of squeeze it. It's like the toothpaste thing. It ends up with a tensile force that pulls up. You know, so the toothpaste comes out of the tube. So that's the same thing. So then you just say this could be generalized in the three areas. The tensile is one of them. That was done by the guy named Pincus. So he's at UC Santa Barbara. He's still around. He's old, but he's still kicking. So he invented the tensile blob. Then the other two kinds of blobs, the thermal blob was more or less described by de Gennes, and the concentration blob by Edwards in the UK. Edwards was a Cambridge guy, and de Gennes is the Nobel laureate from Paris. Right? So those two had to do with this business. If you have your coil, so say you have a coil, and then it's gonna go through this transition. So the concentration blob is kind of the simpler one of the two to understand. So you're going through this transition. So you have R versus temperature for a single coil, and then it goes through this kind of gradual transition, and then it's collapsed. And then there's a theta temperature, and then it's expanded. So like what happens here to it? Right. So the idea is that, and the other thing is you say that you have two states. You have dF is 1/2, and you have dF equals 5/3. So you have the theta state and the expanded coil state. And there's basically, you can't have anything else according to the Flory-Kriegbaum approach. You either have expanded or you have theta. So why is it that you see this gradual transition? And we figured out that we could do that with this. If you say the excluded volume is 1/2 minus chi, then and chi goes with 1/t, then you can explain how this behavior happens, but you can't say structurally like what is the coil behaving, like why does it follow that curve? Right? This VC 1/2 minus chi can give you the size R as a function of temperature, but you can't say how it happens. Right? So this idea of the thermal blob can answer that question. And so the idea of the thermal blob is that the local things collapse first. So the thing starts out with a Kuhn unit, and then the Kuhn unit becomes Gaussian beads, and the Gaussian beads form a expanded coil walk. And as you lower the temperature more and more, those beads get larger. But it's still until they're finally the whole chain at the theta state. So this thermal blob size, as the temperature drops, it gets bigger. So it's going to be kind of related to temperature. Right. So that's kind of the idea of this. So the thermal blob size in here, it's down below, but so that's one of the blobs, is this thermal blob. The other one is the concentration blob. So you have tensile, thermal, and the concentration blob has to do with what happens when you go above C star. So you have the coil, right? The coil's in a good solvent, so its dF is 5/3, and then it's carrying around with it this C star concentration, n by R cubed, right? And so it's n to the 1 minus 3 by dF is this C star, the concentration within that coil. So, so what happens when so you start out in semi-dilute, and then you go to semi-dilute where these things all could touch, right? And then you get to this semi-dilute regime. So at that point, at large scales, the thing goes to DF equals 2, and at small scales, if you zoom in, it's still got this 5/3. So it's the opposite of, so if you have large, small, and then you're looking at the fractal dimension, so you have the tensile blob at small scales, it's Gaussian. At large scales, it's 1. If you have the thermal blob, at the thermal blob at small scales, it's 2. At large scales, it's 5/3. And then for this concentration blob, you have the opposite of this. You have at large scales, it's 2 because the chains start to touch each other, so it becomes Gaussian. And then at small scales, it becomes 5/3. So if you zoom in, it's still in a dilute condition. I see that there's symmetry to this thing. Like you have 5/3 and 2 swap with 2 and 5/3. And then if you look at the tensile blob where you're pulling from the outside, you can think of the Kuhn unit as also a type of blob. And in that case, the small scale will be 1-dimensional and the large scale will be 2. So you have matched pairs here. So between the Kuhn unit and the tensile blob, they swap, right? And then between the thermal blob and the concentration blob, they swap. So you can think of the Kuhn unit is like internally, so you apply some kind of force internally, like it's the rigidity of the chain, and that manifests to the large scale. Whereas the tensile, you're applying a force externally, right? So you're pulling at the large scale and then the small scales like this, right? So this is an external, and this is internal force, right? Or field, force field, right? So you can kind of look at these things as how is the thing applied to the structure? If it's internally applied, then you see this 1-dimensional at small scales, and then it's Gaussian at large scales. It's externally applied. You see the 1-dimensional at large scales and the 2-dimensional at small scales. Then here, so following that along, you could kind of say that the well, depending on how you want to look at it, but the expansion, so the thermal expansion is happening locally, and the concentration expansion, or the thermal expansion is happening on a large scale, but the thermal collapse is happening locally, and then the concentration collapse is happening on a large scale. So this is like external, internal collapse. Right. So to depend on if you can think about the thing as whether you're doing it, how you're applying your field to the material, that can decide the order of these things. And the other thing is that they always come in pairs. Like these things always come in pairs. So you can have, there's always an analogous blob that's coming from some other root, you know. Anyway, so why don't we quit there? So I'll kind of finish up the blobs tomorrow. So there's kind of 2 weeks left since we skipped Fridays. So we'll have a quiz next week. Then the last week, depending on how the grades are. So, whoever gets an A, like going into the last week, doesn't need to take the final. But if you don't get an A, I guess you have to take the final unless you're happy with the B. So, next week, basically, we'll see how it goes. Like I'll check at the grades. Since I don't get the grades till Monday, I won't be able to tell you till like Tuesday, the final outcome of this thing. Right, so that's kind of how we'll go. But so I'll finish up this blob stuff this week. Then I'll talk a little bit about dynamics next week, like the Rouse theory. And that should be pretty good. So any questions, anything? So yeah, I'll see you Wednesday then.
Professor, real quick.
Hi.
This is Charles V speaking.
Yeah.
I had a quick question about grading.
Mhm.
I was under the impression that a group submission would be okay and we didn't have to submit it individually.
Yes.
That hasn't been the case for my assignments 6 through current. I
Uh-huh.
wonder if that has to do with me being in the, all other Canvas section.
I don't know. I'm not sure what, yeah, I haven't really kept track. So you've been getting grades, right?
I got grades for the first 5. After
Mhm.
that, they're just listed as missing.
Oh, okay. So but did you turn anything in?
I contributed to the group, and then the group turned it in.
Oh, that's okay. So did you tell me what group it is?
I'm with Marie Claire. I'd have to look up.
That's all right. I remember that now. Yeah. Okay. Okay. So yeah, it'll just be going with them then. So, but you don't know what grade they have?
I don't remember offhand. They've mentioned
Let's see.
they've, they've mentioned what grade they got on the different papers, when we were talking, but
Uh-huh. I can look here. Uh, the thing is, this is running because I'm on Zoom or something. And it's because I'm using this thing. Like it's because of this QuickTime. That's why. Let me quit that. Like QuickTime somehow, even though it's an Apple program, it like seems to eat up a lot of like whatever.
computing resources.
It just slows everything down. Yeah. When I'm projecting on it, yeah, it slows it way down.
Huh.
Yeah, I did that. It seems to run okay, but it just I guess the graphics or something slows it down. And it's still going slow. I quit that, so there goes that theory. Let's see. All right, it's almost there. It's blinking like it's almost there. Let's see. So, all right, now there's a lot. I have 4 classes. So I got 6 is the grads, 5 is the undergrads. And I'm looking for
The MTEN class.
yeah, but that's not where your grade is. It's in the CHE, right?
I
You're
don't
in,
think
you're in the 5134, right? MTEN,
yes,
right? But your grade is in CHE 5134 with Marie Claire.
correct.
So I have to go to
And
Marie Claire's to figure out what your grade is.
mm,
Uh,
yeah,
so it's slowly getting there. I'm close. I think I'm
don't worry
about 2
about it.
minutes from getting it. I think everyone's getting an A though, as far as I can see. But let me just get an actual number here. Okay, so she's got 88.83% right now. And so it's a 1 boost grade, right, for undergrad. So that would be a 98.83. So that's pretty solid A. The last one they got 105. So I can read you off the grades if you want. I can just copy this and email it to you.
That would be preferable.
Let's
Yeah.
see.
I just saw everything was listed as missing on Canvas, and I wanted to make sure, the whole, hey, you're in a separate Canvas section wasn't screwing me over.
Oh, it should be okay. Okay, so I'm gonna send it with no information, just so in case I send it to the wrong Charles Veith. How do you pronounce your name, Veith? Or,
Veith, yes.
so anyway, I just sent it to you. It's got just the, and it basically it's quiz 1, 2, 3. They don't have numbers on them, but that's the grades. So if there's any dispute, you have a copy, at least, but don't be a dispute. But
All right. Thank
yeah,
you
so
very much.
yeah, it's a pretty solid A right now. I don't see how that's going to change. Like you could have actually average in a 0, and I think you'd still be above 80 because it's 14. So it's only going to drop by like, actually it would be exactly 80, I think, if you got a 0 on the next one. So you probably won't get a 0. So because it's going to be like a tenth of whatever, it would end up being about an 80,
Hmm.
a little bit more than 80. So it'd be an A even if you get a 0. So basically you got an A, I think. I'm pretty sure.
Well, I don't intend to get a 0, so,
Yeah.
but
Who is
that's good to know.
There's one other though, right? Who's the other person?
Oh,
I can look it up, but if you I just let you might know. I'll look it up.
I have the thing open. It's Wesley Black.
Oh yeah, okay. Wonder who he went with. Anyway, let's see. Everyone in that other group must have an A. Let's see. I mean, everyone's over 80, so everyone's got an A, so he's got an A too. Doesn't matter what group he's in. Because it's 1 grade boost, everyone's above an 80, so it should be fine. And it's just a solid grade. There's no A minus, whatever.
That makes it simple.
Yeah, so you should be okay. I mean, we used to be that way, so I just kind of stuck with it. I didn't really see the point in going to the half grade business because there wasn't really any distinction, And also, like, there's no A plus, so it isn't really fair.
Yeah.
So anyway, that's how it is. So you're okay.
All right. Thank you very much for
Right.
clearing up that confusion.
Yeah. All right. Yeah. All right. So I'll see you later.
All right. See you later. Enjoy your day.
You too.
All right. Bye.